Hey there, this is Bernie Woodland. I'm starting a series on C programming. I've been a C programmer since 1987, and I mean, not just as a hobby, but I've used it in lots of different embedded products, different environments. And I noticed that there's a lack of new material being written about this language, which is still heavily used. All the good books were written in the 80s and 90s, and nowadays it's hard to find just material on C. And books that are in college courses which cover C++, even though C++ is almost completely upward compatible with C, they just assume that you know all the basics of C, but where are you going to learn it? So with all that in mind, I've decided to share some of the things I've learned over the years, and I've got my code running in all sorts of products out there, and real-time embedded products mostly. I've used C all over the place. So you're going to learn things that I had to learn the hard way. So before I begin, I'm going to give my shameless plug for the Raging distribution, ragingdist.org. Follow that link over to the Bitbucket Git repository for NUFR. Sweet little RTOS, if I might say so myself. And it's all open source. It's got all kinds of documentation, reference projects, that the things that you can fire up and run on Linux. You can run this with all free tools. You can run this stuff, some of it in simulation environments, including QEMU. It's all out there. Get your hands on it. It's a great little RTOS. Now, I'll start with where C started. C came from this group at Bell Labs. I say the group at Bell Labs. At the time, in the early 70s, Bell Labs was one of the premier research R&D facilities in the world, and you had a lot of guys who were on the cutting edge of computer science who worked there, and this collection of really geniuses produced not only C, but they produced at the same time Unix. But the creator of C, one of that elite group, was a fellow by the name of Dennis Ritchie. And that group includes Kernighan, who helped pen the book, the C programming language, which is a well-written book. And then Stroudstrup later on, who developed C++. These guys really knew their stuff. They studied programming languages. They were up on all the programming languages of the day. So when they created C, they took all the things from other languages that drew on all the different languages which are out there, and then added their own stuff. So, but one thing you have to keep in mind about C is that Unix and C were developed concurrently. The Ritchie creating C, of course, but Ken Thompson created Unix. And the C was originally made to write Unix in, because you get tired of writing things in assembler. You want to port your new OS over to other platforms. They did a lot of porting back then, by the way, of the things written in C. There was a lot of dissimilarities on platforms, which I'll get into later. These were originally developed on the DEC PDP-11 and then later ported over to the the PDP-7, later ported over to the PDP-11. These old DEC machines, these are classified as mini computers. You can Google them. They're about the size of a refrigerator, maybe a small refrigerator, maybe a large one. You can gang these things up together. Interesting little computers. They were not as big as a mainframe, but they didn't have the useful PCs back then. So in the early days, these PDPs were expensive and were hard to get your hands on, but they were not as hard to get to get a hold of as a mainframe. So with this whole development on these machines, there are several things that came out of this, not just C and Unix, but of course using case-sensitive languages started at the same time. So you see that both Unix and C started a case-sensitive type of syntax because they were developed concurrently. And this case sensitivity we take for granted nowadays in languages, but for those of us who are old enough to remember the older languages know that the Fortran and the like were not case, they were just all uppercase. You can read these old Fortran source code files, look like somebody's screaming at you because it's all in uppercase, but that was the norm. So these were the languages that, at least the ones I have listed, and other people will argue for things like Forth, and I'm not gonna say this is definitive by any measure, but these were the languages where most of the high-level stuff, or say most of the code, was being written. COBOL and Fortran were like the first two programming languages. I guess you can throw in ALGOL too. I just threw in ALGOL really to round out the list, and because it's a lot of the concepts were used in C. But the COBOL and Fortran and ALGOL and, okay, we'll say Forth, were started in the 50s, a revolutionary concept of having a high-level language, that expressing what you're going to program in a language which is abstracted from a machine was a breakthrough in computer science. But these early languages were developed in the 50s, and a lot of things were learned between the 50s and the 70s. Not only things that were learned, but the languages had to work around hardware restrictions and the lack of resources back then. And so, but in spite of all that, these languages, even with the time that C was written, were still in heavy use, and there weren't any other languages really to push them out. You had a lot of financial stuff in COBOL. You had Fortran was just all over the place. It was scientific mostly, but they had a lot of embedded products written in Fortran. I've worked on some of those. Pascal was popular in universities. BASIC, which people, of course, who used BASIC ridicule it, but BASIC was a predecessor to a lot of what we call the managed or interpreted languages, such as Java, Python, C#. The concept of that started with BASIC, and there was actually, it wasn't just a hobby language. There are a lot of applications which were written in BASIC. And of course, there were a lot of assembly languages, like on the IBM, what is it, the 360 or whatever series. You had to program a lot of stuff in assembly language, and a lot of other machines, you had no choice but to program things in assembly language. So all these early languages, though, had problems, and this led to the development of C. I'll say C is it is an improvement over language B. There's actually a language B. Don't know if there's an A. But Ritchie set about solving the problems of those languages that I listed before, and studying all the other languages and the developments in the other languages to come up with a language which didn't have these problems. But anyways, what did these languages have as far as problems? Well, the first thing was that there was no standardization of the languages. So we take this for granted nowadays. Take it for granted that a language like C or a language like Java, and you could, so like you get into Python, and Python had a version 2 and a version 3, and a lot of people don't like the fact that 3 isn't compatible with 2. But back in the Wild West days of the Fortrans and the COBOLs, these languages had all of these different varieties. Let's see, I've worked on a Fortran before Fortran 77, and 77 took a long time to be adopted, but you had the Watt5 compiler, the Watt4 compiler, the who knows what other compilers that were out there. And not only did you have all these different flavors of Fortran, but you also had everybody who made a Fortran compiler had proprietary extensions to that language. And they actually bragged about their proprietary extensions. They used these as a advertising leverage, or an advertising advantage over their competitors. Our language can do this and that because we've added all these extensions to it. And with these older languages, you had to have extensions because they couldn't do system programming like C can. There was too many limitations for these things to be used as system languages or whatnot. And then there were optimizations and all this other stuff. So these extensions, though, when you use them in your code, you get your applications are tightly coupled to the extensions, and you try to port that over somewhere else. And between the differences of Fortran compilers and these extensions, forget it. You just can't port the languages over. But this was commonplace up until C. When you wrote code, you wrote it for not only a specific variant of a language, but a specific system it ran on. And if you wanted to bring it somewhere else, well, you get to roll up your sleeves and do the hard work of porting it. What are the problems? Well, it's problems with syntax. So one thing that C has, or didn't exist in languages, was the concept that you have a stream of ASCII characters, and that is your source file. This is all revolutionary with C. In other languages, you had statements, or like in Fortran, you had statements, but you all had like a line of code, then followed by another line, followed by another line, rather than looking at this as one long stream. Furthermore, the older languages were written on computers that didn't have the like I guess you call it sophisticated, didn't have keyboards that had a lot of different characters. They just had your A through Z, numbers 0 through 9, your slash, your asterisks, your dots, the commas, and parentheses, and that. But there were a lot of symbols which were missing on hardware used for these older computers, and a lot of the older languages had to work around lots and lots of different computers that had the limitations on what their keyboards could do. So they had to gravitate towards these common denominators and cut out a lot of the extra characters. So with this lack of the basic use of ASCII characters and the view of this as a stream, this was a pain in the neck for those programming. This is one of the reasons why something like COBOL was so wordy. Instead of using operators and things like that, well, it's the philosophy of the language, of course, but these languages were just a pain in the neck because they didn't use the symbols and they didn't put things in streams, etc., etc. The source code written in punch cards, Fortran going back to the beginning in the 50s, had columns, and you had to adhere to these column limitations, and you could use, start in column 7, start your source in column 7, ran to column 72, and that stuff propagated through the language for years and years. Once you define that in a language, to break from that is a break in compatibility. And I don't know if the latest Fortran standard has got that fixed, but the earlier Fortran, Fortran 77 included, well, it's all column based, not stream based. So there's also the problem where the syntax of the language, when they made the abstractions of these original languages, they were probably being a little bit too abstract. Well, hard to imagine in the 50s being too abstract, but they didn't look at this from say there's a Unix utility called Yak, a Yak perspective of what the parse tree would look like if you had to define it in Yak. and so that made the languages inefficient. There were also library restrictions because you didn't have a concept up until, oh, I don't know, the late 70s of a file. You didn't have a concept of this programming language being able to interface to the operating system to do certain basic operating system input, output, file stuff. And so this is an advantage of C being coupled with Unix, is that it picked up all of the advantages of Unix being file-based, where a file can be any generic thing, and also memory allocation and all the facilities that Unix offered that got put into the C library. Other languages didn't have that, and the library became standardized, and it forced those who developed, who ran C, whatever OS, to provide these facilities, to provide these from the operating system. But your proprietary libraries would make up for these limitations, but there was no standardization on them. So if you wanted to open a file on this particular version of Fortran, this particular version on COBOL, running on this mini computer, you'd have to rewrite that stuff if you put it on a different mini. So another thing is that these early languages were made for what I call batch programming, where you run you make an application, you run it once, you gather input, you produce output, and then it's finished. You're not running this as a daemon. You're not doing anything challenging like you would with an RTOS nowadays or an embedded system. But the language was made to be run like that. It was also difficult to work with these older languages because they didn't have the modules broken into separate files. They didn't have the concept of having, and this is one thing, say, that Doom Pascal, you didn't have multiple source files that you could compile independently and then link them all together. And this, when the code base grows, this becomes a bigger and bigger problem. You're just making a small application. It's not so bad. It gets bigger. It's hard to make libraries, all this stuff. And all these problems in these early compilers, a lot of this led to the compilers being larger than they needed to be, less efficient, bloated. And when you had a compiler which was this big and had so many little non-structured, non-symmetric hooks put into it, you couldn't run this on a smaller system. You had to run your compiler on a large system. I remember in the 80s, the first time I could compile a high-level language on a PC, is like, wow. I could never dream that I could compile and run anything on something that could sitting at my desk, because compilers up to that time was just assumed you'd run this on a mini computer or on a mainframe, because you just didn't have the power to run this, and this was a problem with the languages that were too complex. And this is one of the reasons why C took off. I'll get into that later. When Ritchie sat down to make C, he addressed this. The older languages had some weird or irregular things in the calling procedure. So one of the things that C, of course, did was to straighten that out. I'll talk about that later. But if you look at the way that these languages had to do their procedure or function calls, it was inconsistent between languages. It didn't have the capabilities that you needed in just a basic function call. You had lack of data types. You had common blocks in Fortran instead of externing the data no bit operators, no type of memory management, no concept of being able to malloc a chunk of memory at runtime, no static auto global variables where you can define a variable, not only define a variable, but how it is laid out in memory. All of those problems were addressed by Ritchie in his group when he made C. So what are the advances made by C? Well, of course, the advances are he solved all the problems that I listed before, and portability was one of the first ones that he addressed. C was one of the earliest languages that was intended to be able to run identically from one machine to another. And this was a breakthrough in languages. This was the people, when people talked about C, and they see this in older books on C, they put a bullet point saying C is a portable language. Portability, the word almost came into existence with C because the concept was so foreign with all these older computer. People are just used to writing program for a specific machine. That's just the way they did work, and they didn't think anything of it. And so when Ritchie came along and said you can port your stuff from one machine to another and it'll work identically as long as you understand the restrictions, that was a big wow. And this ability to port from machine to machine, and the thought that Ritchie put in to make sure that it worked on, and the machines that he originally ported this on, they had some crazy architecture, things that weren't 8-bit type machines. I say 8, 16, 32-bit data sizes, data registers, and other stuff like that. He had a tougher problem than what we have today because we have more homogeneity between, especially between general purpose CPUs. But Ritchie did a great job of ironing out and defining the portability, and that's also included and necessary to do this was these features, these libraries, which the standard C library, which had some OS type hooks to allow you to do things that I described before with memory allocation, file, etc. And then when he defined the source code, he was sure to have a tight definition right down to the stream definition of a source file, which I put here in this slide, that's the /n character, which is the character to start a new line. He defined that as a white space. Nobody cared about that stuff before. You just worked around the limitations of the computing language. So the compiler is also a parser and scanner friendly. That's Lex and Yak. They used Lex and Yak in C. They defined the C compilation with these two tools. And I don't know, they might, up until at least recently, I don't know if they still do, but they continue to use Lex and Yak to parse and scan a C file. In order to make an efficient Lex and Yak parser, you have to view this thing as a stream, and viewing this stream as viewing the source file as a stream means you throw out the line numbers and column numbers and all that other stuff, which was a real pain in the neck anyways. You didn't realize it was a pain in the neck until you came over to C. So those of us who use the Fortrans and the COBOLs and all that stuff, you just didn't know any better. You start using C, and they start to teach you this language and how it's laid out and how you can do a hello world program, and you can put things on the same line, break them into different lines. You know, you just got the semicolon, which defines the end of a statement and not the fact it goes on another line. It's a new world. It's an eye-opener. And then also defining the ASCII symbols. that you use, and using these instead of keywords, the whole syntax was cleaned up. The character set was part of the PDP system. The character set came from the VT100. I don't think the VT100 was the first terminal, but it became the de facto standard in terminal emulation. And this VT100 actually is the predecessor to the IBM PC keyboard. The VT100, it basically became the keyboard we use today. So standardization was taking place in hardware, and the standardization was happening with the PDPs. The Unix and C developed on the PDPs that took advantage of that standardization, and they were able to use the full ASCII character set, or rich part of the ASCII character set, case sensitivity. You got everything, the carets, the tildes, the braces, and all this stuff that made the code, that made the source code more readable, and it gave them the ability to add features without it getting ugly, without having all this ugly wording and things like that, like the bit operators and all that. Couldn't have done that. If you did that in words, it would have been a mess. The function calling conventions in C was and still is a big breakthrough. You saw this in earlier C books, this idea of call by value instead of call by reference. Call by reference is what Fortran used. Call by value is what C uses. Call by value is it's copying a parameter into a function with the idea that the parameter will be destroyed by the function, and then using that in conjunction with pointers to give you the referencing powerful feature. It was also that's this function calling parameter maps to CPU. This is the way CPUs work. It maps to CPUs well, so that the what's going on in the language and what's going on in the CPU are very close. Ironic that the earlier compilers, like I said, were more abstracted from the hardware, and C, which was a later evolution in computing, actually brought the language down closer to the way a processor or a CPU actually worked, instead of being further away. You would expect the opposite as time went by, but this turned out to be a great idea, and one that caused the language to become what it is today. And with this function parameter conventions, this worked out incompatibility problems, because compilers when you look at some of the differences in Fortran compilers and you got into the language closely, they were loosey-goosey, or they didn't have a tight definition of how some of the function parameters should be passed. And this is a real problem when you go to port from one machine to another. And of course, the optional return value and the way it worked is part of the calling convention. All of this was a huge improvement that C brought. And like I said, with the pointers and the indirection, the system of that Ritchie devised, or saying Ritchie devised, or saw from other language and decided to put in C, the pointers and indirections are just, it all just works together. The syntax, even today, it's like one of the most powerful features to C, and it's so close to the way a CPU works, the way assembly language addressing schemes work and instructions, the way that stacks work. Let me move on. The differences in the storage classes of variables, the ability to define a variable as an auto storage class, static, global. You can choose how the underlying architecture will store this variable, whether it will be temporary and put on the stack. Again, this storage is close to what the machine does, and it's also close to what the OS does, the OS being Unix in this case. The architecture that a person would use in their computing language is all like a reflection of what the whole OS and what the machine does, what the CPU does. When programmers got used to programming in this way, they could write some really tight code which could approach speeds of assembly language, and they cut out a lot of the need for having to resort to assembly language because you had enough control at your fingertips. So the function calling parameter, all these features of C just work together. The linkage model was, or the concept of having different modules that all get linked together that can be compiled separately and have this managed by the operating system. The operating system, you define a source file as a text file, and you can use these standard tools to link. You could do these with, like, of course you could do this with Fortran later on and all that, but it wasn't built into the language from the beginning, and that's the big difference. So people will say, well, yeah, I've compiled and linked COBOL and Fortran and whatever languages, but the language itself wasn't made that way from the beginning. So when you make a language that's got all these concepts built into it from day one, you come up with with something that works in modules better. And also the include files, the preprocessors, are the use of the preprocessors. Nowadays the people look at header files, and in most newer languages they've gone away from header files. So header files were a big breakthrough. Not only header files, but all the header files are one part of the whole preprocessor capability. The preprocessor is the idea that you scan the files with these preprocessor commands first, and you produce a single processed source file, and then you compile that. So you break your compilation into expanding the preprocessor directives, which means sucking in include files, expanding pound defines, expanding macros, doing conditional compilation. The output of that is a single long file, which then gets fed into the compiler. So the compiler never actually sees the preprocessor. And actually on older compilers, the language was, or the implementation was such that you ran different phases. So if you compiled a C file, you would run a separate preprocessor, then you'd run a separate compiler, then you'd run a separate, and a lot of times in the older compilers would generate assembly code, then you'd have to run an assembler, then you'd link all those things together. So the compiling was broken into different steps. The header files, which are nowadays, you look at C++, and all this stuff with header files is a mess because the language was built on C. It's painful to program in C++ because of header files, but not as bad with C. Still is a pain, but at the time that they developed, that Richie started the programming community to use header files, this was a big breakthrough, because now you can put something in a common source file, in a .h file, and share it between compilation modules, share it efficiently. Like I said, other programming languages allowed you to add header files later on, but at the time they didn't have that capability. Most of them didn't. Now, one of the interesting things that Ritchie did when he made C is that he decoupled the standard library from the language. This was also a difference from the legacy languages. To this day, if you program C on a DSP or something like that, you might not use the standard library at all. The C is modular in that you can put in your own library, but it is also standardized where if there is a one standard library, everybody can use. And I've talked about all the things that you can do from Unix already. Didn't mention things like signals and things like that, but you get the idea. There, of course, were other system programming features in C that had to be put in there because Unix was the intention of writing the source code for Unix was the goal. You had to do everything you could do in a system programming language, and really everything you could do in assembler, just about everything. Not everything, that's not true. You can't do everything in C that you could do in assembler. But bit operators were put in there to make up for the what you could do in assembler that you couldn't do in most high-level languages, at least not in standard form. Then having this main entry point as a point to enter your program from your OS. These made C an attractive programming language for systems that cause developers to latch on to C, and this is one of the factors, and there are many which caused C to succeed. But when you add all these things together, what I just said, you basically had a language which solved all the problems of existing languages up to that time. Now, there was a few weaknesses in C, especially the early implementations that other languages had strengths on. I mean, just what comes to mind is the floating point support. It's not as good as Fortran. It didn't have some built-in types. It didn't have a built-in bold type and things like that. But putting those things aside, solving all of the problems which I mentioned before caused C to take off. Because on older systems, you had this mindset that you were going to have to customize all this, and once people saw that you didn't have to customize this stuff, you could share code out, you could develop on one platform and then run on another, your productivity started going up. And this is the productivity advances to this day are the goal of computer science evolution is to give you greater productivity. You look at all the changes in languages, starting from C, going to the Javas and the C sharps and everything else. It's all about productivity enhancement because it's no longer cost feasible to develop this highly customized batch-driven application that runs on a mini or a mainframe. If you had teams of engineers working on this stuff and we didn't want to pay their salaries, there was with computers shrinking in size and they're having more RAM, there were more applications which were opened up, so they needed to have more programmers. They just couldn't develop the way that they used to. Those old development paradigms just weren't going to work. And so with C solving those problems and those productivity enhancements, people just grabbed the language and started running with it. Now, those are all well and good points, and I think those are enough to make C popular and to push out other languages. But on top of this, the C compilers were really slim. The oldest IBM PCs, you could run your C compiler. You might have to break it. You know, you've had the various stages. Some of the older compilers, you had a 2-pass compilation, and to run this on the early PCs, you might have these 5¼ inch floppy drives, which are only big enough to house one pass of the compiler. You might have a preprocessor and one pass, the first pass of the compiler, then another floppy disk with a second pass, and then a floppy disk with the linkage and the assembler you could throw in somewhere there. But breaking the compilation into different stages means you could do this on several different floppy disks. And yeah, I know it's silly nowadays thinking of having one floppy disk you put in, pull it out, put in another one. It's tedious, but you could compile a high-level language on a PC. That was revolutionary. Just the ability to do this and break into the PC with the PC, say, platform with a language which could be compiled on that was huge. As PCs started to take off in the early 80s, the C compiler was just made to fit into those relatively smaller platforms. It could squeeze in there where the older languages could not. And of course, like I said, the C being a system programming capable language, system programming includes embedded programming, real-time programming. You could program things in C and make it not only program in C, but make it portable that you couldn't do in other languages. You had to control memory. You had to do this. You had to do that. C could be and still is capable of doing just about everything assembly language does. So another thing is that with this capability pushed out all that assembly language stuff, because a lot of the older languages like the Fortrans and the COBOLs and that required you to write something in assembler just to make up for the deficiencies in the language. So if you couldn't do something in Fortran, it's like, yeah, we're going to have to do this in assembler because we've got to get in and do this thing on the, our common block stuff doesn't allow us to allocate memory or et cetera, et cetera. So yeah, we'll have to program this in assembler. You can see what a pain in the neck that was. And C being and in the early days, some people would, instead of calling it a high-level language, called it a medium-level language because it was not as abstracted from the way that the CPU worked. It was closer to the real operability of the CPU, and this, by the way, still is an advantage of C over other languages and makes it popular and really hasn't been replaced. But this stuff is these features of C, which worked closely with the CPU, with the improvements in compiler design, allowed writers to write code which was almost as efficient as assembler. So nowadays, if you know how to write efficient C code, and it's not just a writing efficient C code, but you have to be able to set all the compiler flags correctly, things like that. But you can write as a general purpose code. You get into things like memset and all that stuff, and yeah, that's a different story. But general purpose code, you can write efficiency-wise in speeds which come close to, say, that are 50% or so, that come close to the efficiency of what you would have with assembler. So it was not only a CPU efficiency thing, but remember, RAM savings is also important. So there's a trade-off between CPU's efficiency and the amount of RAM that an application uses. So having like auto storage class variables saves a lot of RAM. And when you save RAM, that makes more RAM available. And when you have more RAM available, you can write more efficient programs, because when you're writing tight algorithms and that, you can trade off, since you can trade off A lot of times the algorithm can trade off the CPU efficiency and the RAM use. Basically, if you throw more RAM at a problem, the CPU doesn't have to take such a contorted path to make that solve that algorithm. So the no runtime environment where you have the lack of an environment where the language doesn't have to run on any sort of engine. It doesn't have to run in this layer thing, which C doesn't have a lot of competition with nowadays. C, what you write in C is just about what runs on the CPU. In a managed language, that's not the case. The language you write goes through all these different layers, but when you get to describe a language in a way that's very close to the CPU, you're going to write really efficient code. Developer becomes the one who determines how efficient the code is going to be. And this can be tedious, of course, and that's why we have the managed languages, but as far as efficiency, you can't beat it. So what paths did C take in its evolution? How did it get from the original standard? What was the original standard? Well, since C was developed in the early 70s, it wasn't, the first standard wasn't until 78 when Kernighan and Ritchie wrote the C programming language. A very well written book. It's still an excellent book, and if you're going to learn C, it's still one of the best references on the language, which I'll just throw out there. If you're going to get 2 books on C, get a C reference manual by Harbison and Steele. I don't know what edition it's up to. And get the C programming language. Between those 2, you'll understand the language pretty well. You won't understand how to use it to a large extent, but you'll understand how it works. But this book being a great book, not only caused the language to be standardized, but got a lot of people educated right out of the gate. It's a small book, the C programming language. There's been a whole generation of programmers have gotten their hands on that book and learned how to program in C and learned other concepts in other languages. So the standards in C started, of course, the publication of the KNRC in 1978. That led to ANSI C, which was the first real standard of the C language. So the KNRC cut a lot of corners, and I'll have another video to talk about what has in KNRC has been deprecated, but there's enhancements and improvements that were made in ANSI C. Most of the C that we program in today is pretty much ANSI C. And I lived through this whole era. One thing that I'll note is that the language was proposed as early as 87, and it was adopted by compiler makers pretty quickly and adopted before it became standardized in 89. So the ANSI C history goes back a little bit before its actual adoption. And of course there were some compatibility problems, and there was partial adoption in that, but everyone saw the advantages of ANSI C. ANSI C was a well done standard. I only wish that they did a little bit more, but so they fixed problems in the original KNRC that could be fixed, and some of the problems they couldn't fix because of compatibility. But ANSI C did a lot to extend the language. So the language needed to be extended from the KNRC for a couple of reasons. First reason was that the KNRC had to be super efficient. So Ritchie cut out a lot of features from the language so that he could fit this into a small compilable footprint, so the compilers could be simpler, so that it didn't take such a massive system to run a compiler on. He did it because it was quicker to develop C this way. And at the time, and with these shortcomings, there's always workarounds in that. I don't think Ritchie realized he's making a language that was going to last for 50 years. And even if he did realize it in the 70s, what could he do? He had to get traction on that original language. And he had to cut some corners. Now, the last, say, major standard is C99, which was adopted in 1999. There have been other standards after that. I don't like them. I don't use them. I don't write code to them. Really not interested in them. And unfortunately, C is starting to get into this problem that other languages are, where they have to keep themselves current. So every 3 years they come up with a new version of a language. So it looks like they're starting to do that with C. I think that's a mistake. I think they should just freeze the language on something between C99 and ANSI C. There's some things I don't like about C99, that it's like incompatible with C++ in a few ways, but apart from that, there's a lot of improvements that they made. Unfortunately, not all compilers. I think the safe thing is to make something run in ANSI C. And what comes to mind is the Microsoft, something that'll, this being a little bit later, but some of the early 2000s, mid 2000, let's say 2000, 2010 timeframe, Microsoft C compilers were ANSI C, and true of other compilers, the C99 compliance wasn't taken as seriously. So when they went from KNRC to ANSI C, everybody jumped on ANSI C. When they did C99, well, they already had some improvements, like with the // but most people said, we'll get around to doing that when we get around to doing it. So like the C11 and the C18 standards are some of the others that I mentioned. And like I said, I really don't even know. I mean, I've glanced over those standards. I don't know what those things have in them. But I put down this second thing as a pseudo-standard, and the compilers to define certain functionality in C. So the C language by itself is not the definitive, what am I trying to say? For a programmer, he or she can't just rely on the C language to do what he or she needs in an embedded environment. It's also how GCC works, how the optimizations are, how the warnings are, and like it or not, some of the extensions in GCC and other compilers, these things define the language. And it's particularly important when you get into real-time embedded systems. I've had to face this writing NUFR. I have to rely on extensions in GCC to be able to come up with a kernel which will run as a bare bones, bare metal operating system, operating environment. That the C language itself is not sufficient to do this. And nowadays, people who write C, and since C is used mostly for embedded products, you've got some tools, for fast tools on Linux machines and things like that, of course. But no one sits down to write an application in C. A general application, they're going to write it in some other language, right? You're not going to, unless you're in a undergrad program or something like that. If you're going to do this on the job, you're not going to sit down, okay, we're going to do this database application in C. That the people would fire you if you did that. So what they use C for is being embedded in everything. They use nowadays they will typically run some sort of source analysis tool over the source code because it's a real-time embedded, because it's something that might run in an aircraft or a mission critical thing, something in a car. You're going to want a tighter definition of the language which a source analysis tool brings. So in the early days of C, people used all kinds of tricks and things that C is capable of, but when you add the source analysis tools, which GCC has a certain level of source analysis stuff built into it, some of the warnings and things. The coding standards and style enforcement, all those things, what they do is they limit what type of code you should write in C so that you're not doing crazy things. And then they catch mistakes that about the sophisticated program, and I love Coverity. Coverity is my favorite. CPP check or whatever. An uninitialized variable, something that you're trying to hide a variable, and a variable is defined as something else in a tighter scope inside of braces. These things have become part of writing C, so you no longer just write C code. You use the compiler and the source analysis tools together to ensure that that C code doesn't have the problems that early C code had. So this is reputation C got early on because you could do anything with it, and also because you get a problem with a pointer going over an array bounds and something like that. There were other languages which would catch these things for you automatically, and people criticize C for it. But nowadays, with all these source analysis tools, it's not as likely that this would happen. Also, since C is a fairly simple language, it's easy to make a source analysis tool for. Now, I should add this thing, having been through the 80s and everything with C. C became the first of what I call the language to end all languages. Just like this is a play on the war to end all wars, World War I. What happened after World War I? Well, they had World War II. But this idea that you're going to come up with this one language that's going to be the ultimate language, this idea, like almost to say, it started with C. So the bandwagons, and I hope by this time we're smart enough to understand that you're not going to have a single silver bullet to cure all your programming needs, but C was going to be the end language. This is the last language we will ever need to develop. This will solve all the problems. This is just wonderful, and it is a great language. It's still being in use today, but this idea that we're going to solve all of our computing problems with this wonderful language started with C, and I wish people would stop it. Ada then came along, and Ada was the next wave of the language to end all languages. And then you had the object-oriented crowds, and we're still on this object-oriented kick. I'm so tired of programming languages where you have to make a singleton model, because you have to force this into an object architecture where, guess what, people? Not everything is an object. And so the object-oriented, and this started with got these Smalltalk devotees. Smalltalk is, the whole philosophy of Smalltalk is another evolution in the language to end all languages. You're going to do everything in object-oriented. And if you've gone and read all the object-oriented literature, the people still sign up for this. Then you had the managed languages. The managed languages are the cure for everything, Java and everything. And I'm not saying that these aren't that these haven't made a lot of improvements. These haven't fixed a lot. Obviously they have, but I'm wanting people to stop calling these the end all. We're going to do everything object oriented now. We're going to do everything in Java now. We're going to do all this and this. Programming is not that simple. It just isn't that simple. C has, since it came out, has been a heavy influence on every other language. So even if you don't intend to program for a living or program a lot in C, if you study the language and learn it well, everything you learn in C will get brought over to all the other languages. If nothing else, the syntax will be the same. And the concepts of portability, the calling stack, and all that stuff. This is a great way to start your understanding of how computer languages work, because it's so close to the CPU. If you understand C, then the next step is, how does C++ work? Well, C++ was originally basically the C++ compilers compiled C source code. If you look at C++ from that perspective, you'll understand the language better. But also C, and since it's downward compatible with C++, a lot of the functionality in C++ is just C code. C is still a top language, and if you go into you could look at, you just Google any type of survey they've taken, what languages people still program in. Of course, it's still being used to program Linux for, and in embedded systems, there's all kinds of stuff that you don't see. The routers and the switches and the units in cars and the stuff that runs on little chips. C is all over the place. To this day, a C developer position is still a good paying job. Not just the vanilla C programmer, but somebody who can handle the difficulties of a real-time embedded system or a systems type language for an operating system. So I will have more parts to come, and next time I'll talk about what the deprecated features of KNR are, KNRC. But Bernie Woodland again, and I've got years and years of experience here that I'm going to be putting in these different series, parts of the series. I wish people would teach this more. I wish some of the academics would go over the basics better. Hope I cover all the things though, and join me next time. In the meantime, of course, crack open, go to this ragingdisk.org, go to the NUFR repository. You can hit the ground running. You won't have to pay a dime to do this, as long as you can run Linux, even if it's in a container on a Windows system. You can start writing applications in this thing. Buy yourself a little. I think that the cheapest stuff, even for the 430, is just like, I don't know, $10 or $15 for a reference board. Pay about $40 or $50 or something like that for a ST Micro reference board, and you learn how to program. And I'll guide you through it with the different parts of the RTOS series and all that, so that you get to be an ace programmer. And I'll see you then.